All right, so the recording should have started now, and apparently Mr. Satunga says you left off on slide 20 after Friday's lecture. So we're going to be continuing with work in class, new work in class. But what we're going to do is we're going to use the tutorial periods for revising past papers, which means we can do that this week and next week, which means we can get a lot of revision done and hopefully maximize how well semester test 1 goes without falling behind, because we'll still do new work in class, and I'll upload a non-scheduled extra tutorial which will cover the work that you'll need for each upcoming practical going forward. Although you won't get a new practical itself this Friday, because the following Friday is your semester test, you'll get a practical requiring you to study for your semester test. So do it though, because there is something for you to do in order to comply, but we do want things to go as well as possible. All right, so so you still have a practical due this Friday, the one you got last Friday, but this coming Friday you won't get a new one due the following one. Well, you will, but it'll be to study. You'll see. All right, so just to clarify, since people seem to be having difficulty, we're doing new work in class, and there will be a pre-recorded tutorial uploaded this week and next week covering the new work so that we stay on track. We will be doing past papers in the tutorials, which will be different past papers in each tutorial so that you can attend multiple ones and see different answers. And then you won't get a new practical this Friday, because your test is the next week, but you will get a special practical to study for the test. So hopefully everyone has now understood what I've said. And then let me start sharing. And then, okay, sounds good. And then let's just start off with the code. I don't know. Hammer, hammer, hammer. There you go. This is the code. If you're watching this late, this is what you got to type in. All right, for the rest of us, let's continue. And what we're taking a look at now is the polymorphism. So we looked at simple inheritance before, which is basically just where you have a base class that you can then derive into derived classes. You can extend into derived classes is also the term that's sometimes used, by inheriting from them. And you can change the behavior of existing functions, sort of. I'll show you a worked example of why we need this polymorphic approach in practice. And you can definitely add new behaviors and specify which data and behavior is visible to the derived classes using protected, but it's not perfect. It's not ideal. It does show some flaws in how it works, and the reason why it doesn't work so well is because of C++'s desire to be as efficient as possible. So when you compile your program, C++ needs to map the location in memory where each of the member functions are to the internal function pointers that it uses to store each of the member functions. Just like we did with the pseudo objects, where we manually got the address of a particular function that was implementing a behavior and stored it in a function pointer, the C++ compiler does that as well. But it wants to do it quickly. So what it can do is, for behavior that doesn't really change, it can pre-compute what that address would be. Now, it doesn't know in real terms where in memory you're going to be. So it calculates it as an offset. Basically, it says from the start of the program in memory, wherever that is, move forward this many bytes, and you'll find the beginning of the code in memory to execute this particular function. So these offsets can be pre-computed by the compiler, which means they're really fast to run. And C++ has always had a bias towards trying to be as fast as possible. Sometimes, though, speed comes at the expense of flexibility. So what this means is that if you do inherit from a base class and redefine a behavior, but you call that behavior from a variable that's of the base type class, it won't know what to do. It will just treat it like it was a base type. So in order for that to work properly, you need to delay the calculation of where the implementation is going to be in memory to runtime instead of compile time. And C++ provides a mechanism for that by way of these virtual functions. So a virtual function is basically a little loop, in a sense, where it will loop, it'll store all the virtual functions in an array or a table. It's called the V table, the virtual function table, and it will loop through that table to try and find an implementation for you. And this table is basically structured as a series of linked tables. Each class has its own V table. So it'll look in the current class that you're in, see if it can find an implementation that matches the call. If not, it'll go to the parent, loop through its V table to see if it can find an implementation that matches. If it can, it executes it. If it can't, it'll keep looping up until eventually it hits the base class that everything else was derived from. And because inheritance trees can be deep, that could be slow. I mean, like fractions of a second slow, but still slower than instant. So that's why it's not the default in C++. And you have to specifically ask for a function to be virtual using a virtual keyword. And the power that comes from this is that these virtual functions are allow for you to add new types in the future that your class didn't know about now in the present. And it's very rare that you can write code that's future-proof. It's difficult enough to write code that's backwards compatible with stuff that already exists, but to write code that's compatible going forward with stuff that hasn't been written yet is an incredibly powerful technique. So sometimes it's really worth being that slow. So yeah, this is basically the implementation of how virtual functions work, as I described. Another term for this runtime lookup of the function implementation is known as late binding. So the binding refers to getting the place in memory where the compiled code for the function is and storing it in a function pointer. If you do that at runtime, it's called late binding. And if you do it at compile time, it's called early binding. So it's a very powerful tool in not just object orientation, but in many other dynamic systems. Because what this allows you to do is that it will look at the actual type of a variable, the calling object's actual type, not the declared type through which the you're calling it, but in memory what its actual type is in order to work out what implementation to use. So we use a slightly different term because they are implemented slightly differently in C++ between whether we're changing the behavior of a virtual function or a non-virtual function. If it's a virtual function, we say it's been overridden, whereas if it's a non-virtual function, we say it's been redefined. Most programming languages these days, if you look at the big ones, if you look at things like Java, or if you look at C# or Visual Basic, .NET, or many of the conventional programming language, even ones that aren't very like well defined according to a set of principles, things like JavaScript and so on, they will tend to do stuff at runtime. I mean, things like JavaScript and Python, they only do stuff at runtime. They don't really have a compile time per se. So by default, the most common way of changing the behavior in derived classes is by overriding or doing something equivalent to overriding at runtime. So it's unusual for a language to have this distinction. C++ does. That's why we have those two different words to refer to the two. So I'll show you the difference in an example after we've hit the end of the slides, just to drive home the impact of those two. So why doesn't C++ do that? As I said, it's slow. But slow for C++ is not necessarily slow for most other languages. Most other languages are quite happy to waste CPU cycles to make things easier for the programmer. C++ sort of adopts the approach that you know what you're doing, so it'll try and do things as fast as possible unless you have a reason to do it slower, in which case it's up to you, the programmer, to say so. So overhead, that term refers to the cost you pay in terms of something to get something done. So for a business, your overhead is the cost it takes to run the business, to pay the employees, to pay for water and lights, to clean the place. You don't make a profit off of that, it's an overhead. For an algorithm or an approach in computer science. The overhead refers to maybe wasted CPU cycles that are necessary to make your code work but aren't actually part of your code, or memory that gets used in order to store data that's needed for your code to work but isn't part of your code itself. So virtual functions are worse than normal redefined functions in both of those metrics, because extra space is used to store the virtual table, as well as extra time is used in order to loop through each of the linked virtual tables up the class hierarchy to the base class, potentially, if the root behavior, if it isn't redefined anywhere in the root behavior. And for what it's worth, this loop, where it goes looking for an implementation for a virtual function call, if it can't find one, that's an error. And you'll see this error message probably quite a bit when you're working with virtual functions, where it will complain about the V table. So the V table is this virtual method table that it uses to look things up. And if you see an error about not being able to find something in the V table, it probably means you've defined a virtual function somewhere in your base classes, but you've never actually implemented it anywhere. Or particularly if it's a pure virtual function, you've never provided an implementation for it. So that's a problem. So we use virtual functions when they're needed, because they do come at a cost, but they do allow for things that are literally impossible without them. So sometimes it is worth paying that cost. We saw in the tutorials last week that sometimes you define a behavior in a class that doesn't have any meaning for the most abstract of your classes. Remember, with inheritance, the higher up in your inheritance hierarchy, the more abstract, the more vague, the more general your classes are. You might have as your base class person. What's a person? Well, tell a lot of things about a person, but it doesn't tell you, the fact that you know someone's a person doesn't tell you their gender, it doesn't tell you their job, it doesn't tell you whether they're a student or not, it doesn't tell you whether they can vote, it just tells you that they're a person. So person is a very abstract or vague concept. So if you have a function that relates to people, for example, that they must do something, what does it mean for a person to do something? There are certain actions that all people do, but there are certain actions that are specific to the kind of person that you are. Like a student might study, or a worker might work, or whatever. So it might not be meaningful to have a default implementation of that behavior. For example, in the shape hierarchy of classes we did last week, what does it mean to draw a shape that's just a shape? You can't draw a shape without it being something. Even if it's a squiggle, it's still a squiggle, right? You could come up with a mathematical formula that defined the exact path that your pen took to draw that squiggle. So it's not no shape, it's a particular weird shape. So something like drawing of a shape might be so meaningless at the higher levels that you just want to define that it'll be possible later on. So in order to do that, you make use of a pure virtual function. And as I said before in the tutorial, I really strongly and deeply dislike the notation for it in C++. But the notation is as follows. You define the prototype for the member function. It must be virtual, and then you set it equal to 0. And then you must not implement it in that class, only in classes that are derived from it. And failure to implement it at all would be an error. And a class that inherits from this and fails to implement it, that might not be an error in itself as long as it gets implemented somewhere down the line. But a class that implements it and fails to, or inherits from shape or figure in this case, and doesn't provide a concrete implementation of draw, becomes itself an abstract class. So the implication is, when we have a pure virtual function in our class, either directly or one that we've inherited from one of our parents and haven't concretized, haven't provided details for, then we are an abstract base class. So what does that mean? It means, well, as I said, you've got a pure virtual function in it, but the side effect is that you cannot be instantiated. So you cannot say new figure. You'd have to say new triangle or new square. You cannot say new person. You have to say new student or new employee or whatever, because it can't be implemented itself. It simply exists as a placeholder, in a sense, in the object-oriented design, defining some functionality, all right? But you'll never get objects that are of that type and that type alone, because they're incomplete in their definition. They don't have a full definition for each of their members, particularly the virtual functions. So if you fail to define all the pure virtual functions in a base class that you inherit from, you too become an abstract base class. Now, there's weird side effects for abstract base classes, things you might not consider. For example, when you create a fixed length array of an object type, it actually instantiates those objects using the noargs constructor for each of the elements. So if you've got an abstract base class, you cannot have a fixed length array of that type. You can have an array of pointers to the abstract base class, that's no problem. But you can't have just a plain old array of that type. That won't work. So the whole point of inheritance, let me just see if there's any questions before I carry on. Sounds like a good one. So the announcement that was the scope is on Eve. Oh, okay, this sort of drifted down a bit. Oh yeah, this is also worth pointing out. Why did this not keep track? All right, yeah, that Monday, this coming Wednesday is also a Monday according to the university. So there'll be another class in this slot and another tutorial in its normal slot on Wednesday, because Wednesday is a Monday. That's a university level decision, not a Computer Science 1 level decision. You'll have all of your Monday classes for all of your subjects on Wednesday. So just bear that in mind. Are we continuing working with work after semester test 1 scope? Yes, because there's a lot of work still to do. So yeah, there's a lot of things to do. All right. The scope is on Eve. Yeah, I think you've mentioned that before. Check announcements. Okay, so this was the question. Do I mean the implementation in the derived class? Yes, I do. So if you've got a base class, let's say you inherit from, you've got an employee is a person. So person is the base class. An employee is also is a derived class, but let's say it's got a pure virtual function in it as well about calculating salary. And you won't calculate salary for an employee without knowing whether or not they're a full-time employee, a fixed-term contract employee, a temporary employee, because they'll all have different formulas for calculating their salary or wage or however it's paid, weekly or monthly. So all of those details will be captured in the derived classes. So even though employee is a derived class itself, it derives from person, it's an abstract base class in the sense that it still has a pure virtual function, which means it can't be instantiated. Since we're following a Monday timetable on Wednesday, will the tutorial be available on Wednesday? There's a tutorial slot on Mondays as well. It's in there, so it'll just occur in that slot on Wednesday. This Wednesday is a Monday. That's literally what it means. Is it okay to declare a function and or variable as auto? Yeah, look, it is. So you can use the trailing type definition. You can't not specify the type. So I see what you're saying. So in the most modern versions of the C++ standards, so 17 and 20, you're allowed to leave out even the trailing type part itself, and it will infer the return type of a function based on what you actually return. So you can't do that with the pure virtual function because there is no value being returned there, and it can't work out what auto is supposed to mean. But you can use auto together with a the trailing type syntax and specify that type to make a virtual function, because it's at least defined. Auto, we covered that in semester 1, but it basically is the type inference functionality in C++ that lets it automatically work out what the type of a particular identifier is going to be. So revise Computer Science 1A if you want to see that. We used it for both functions and classes not classes, functions and variables. But I try not to overuse it because we try and write code that's self-documenting. Sometimes overuse of auto makes the code harder to read because you have to look somewhere else to figure out what the type of something is. I prefer, in general, manifest typing. Right, am I correct to assume that we would have used composition and inheritance for the tuts from last week? I don't understand what the context of that is. Your tutorial that you received, that you did involving composition and delegation. I'm sorry, you'll have to rephrase it. I'm not quite sure what you're asking. That we would have used composition and inheritance from the tuts from last week. When would you have used it? I mean, yes, you use it. They become part of the future practicals. So I'm not quite sure exactly the context you mean there. But in any case, the whole point of inheritance was to establish an is-a relationship. And an is-a relationship means that you've got type compatibility. So the base class is compatible with all the derived classes from an assignment point of view and a parameter passing point of view, in that the compiler won't yell at you. If you pass an employee to a function that expects a person, that's fine. An employee is a person, not an issue. The question just becomes, will it behave like an employee or a person in the code itself? And that depends on whether you've written it polymorphically or not. So a derived is a derived class of base, so derived objects can be assigned to objects of type base. The reverse is not true. So let's say, for example, if you've got a function that expects an employee and you pass just a random person to it, there's no guarantee that the person happens to be an employee. That's like just saying, I'm going to open the doors of my factory to anyone because all of my employees are people and doors let people in, and I'm just going to let any person in and hope that they can do the job in the factory. That is, of course, very dangerous. So the reverse isn't true. So a discount sale is a kind of sale, but not all sales are discount sales. You might have loyalty sales, or you might have buy one, get one sales, or you might have other kinds of sales. So the rules for applying sales calculation will differ depending on what they are. You can definitely say a discount sale is a sale, but you can't say all sales are discount sales. And the most common way of discussing these hierarchies is through an animal hierarchy. So for example, and that's what we'll do, if you've got a pet that has a print function that's virtual, and a dog is a pet, right? So all pets have names, and dogs have specific breeds, for example, Alsatians and poodles and all sorts of things. And you want to have a print function that will print out details of this dog or this pet. Obviously, you want the dog one to include the new information you've introduced. Horribly, now bear in mind, this is not an example of good style because this is a public variable. You would never do that because obviously that's bad encapsulation, bad information hiding. But just to get things to fit on one page, licenses are taken. So a dog is a pet. And now we can do stack allocated instances of dog and pet. So if we create a dog variable called vdog, which is of type dog, and a variable of type pet, which is an object of type pet, they are both allocated on the stack. So if I can populate them, as I said, you would never do this with classes normally. You'd have with publicly visible variables, but just bear with me. So we store the name tiny inside the dog object, and we set its breed to Great Dane. Just for what it's worth, if you're unfamiliar with dogs, this is a bit of a joke because Great Danes are one of the largest breeds of dogs, so calling it tiny is I suppose ironic in one of the most trivial senses of the word ironic. And then we assign the dog variable to the pet variable, and this is perfectly okay. A pet is a dog. I can store a dog inside a pet, but, and as I said, the reverse is not true. Not all pets are dogs. You can't pretend that your snake is a dog. You're going to have a bad time. It's not going to fetch very well, and it might bite or crush you depending on what kind of snake it is if you try and play with it like you would with the dog. So this is an example of one of those kinds of the problems that you might have seen in the past papers, particularly related to object orientation. So this is what's known as the slicing problem. Because if we tried to access the breed field from pet, which it should have, because in memory, this dog has a breed name, and we stored the dog in the pet. So can't we get it back through the pet variable? And the answer is no. It basically forgets everything about what kind of thing it is when you did the assignment, because what happens here, in general, pretty much always, a derived class is actually larger than its base class in memory. That makes sense because it's got everything that the base class had and more, so it must take up more space in memory. When we're allocating things like this, we're doing static allocation. We're saying on the stack, allocate enough memory for a dog, and then on the stack, allocate enough memory for a pet. And there's less memory required for a pet. So when we did this assignment, it basically slices off everything that's defined in a dog but not a pet, so that the stuff can fit into the pet variable itself. That's why it's called the slicing problem. So that information is gone. It's basically forgotten everything that made it a dog. It remembers its name because that was part of both dogs and pets, but it forgets its breed because that was unique to dogs. So it's a problem because it's definitely not what you expect to happen logically when you're doing these assignments. But it's a necessary practical requirement based on how C++ works. So how do you get around that? Well, what you do is you make use of pointers, dynamic variables, and virtual functions, really, in order to work around the problem. The problem comes from where the memory is allocated. This memory is allocated on the stack. Remember, your alternative to allocating memory on the stack is to allocate memory in another place called the free store, like we did with arrays. You can make a fixed length array, which lasts automatically, but you can't resize it. It's fixed length. Likewise here, sizes are fixed. Memory is managed automatically, but you don't have any control over what's going on. So if you allocated these things on the stack, on the free store rather than the stack, you'd be using a dog pointer and a pet pointer and use new to create them. You then have the responsibility of needing to delete them later. So that's what you pay when you use the heap, is that you're taking personal responsibility for the memory management of those classes. So here we go. We can create a pointer to a pet, ppet pointer, a pointer to a dog, and then we can allocate a new dog. Right? So in memory on the free store, enough space is allocated for a dog. And when these variables were created, it's only the pointer variables that were allocated on the stack. So those will always be roughly the same size, whether they point to a huge place in memory or a small place in memory. It doesn't really matter. Or the beginning of a large block of memory or the beginning of a small block of memory, it doesn't really matter. Just like you can write the address for a very tall building or the address for a single-story shed on the same piece of paper. It doesn't affect how big the building is allowed to be. Same here for these variables. So we allocated space for a dog on the free store, and then very carefully, and this should be familiar to you from the pseudo-object approach, because this is a pointer to a dog, we need to dereference and access the member. So we use the arrow operator. Then we can set that to tiny, and likewise for breed, we can set that to Great Dane. And now, if we store pdog inside ppet, that's perfectly fine. The memory hasn't been sliced off. It's still there. We couldn't access the breed via the pointer because that member doesn't exist in the pointer. That's still illegal. But at least we haven't had any actual loss of information. We just basically taken an address written on a piece of paper and copied it to a different piece of paper. So to really get this going, we augment this with virtual member functions. So this print virtual member function can access the breed information, even though the pointer is actually to the pointer's declared type is to a pet, but its actual type is to a dog. So this print function can access and output the breed information as well without any hassle. And that makes this function what we call polymorphic, because the behavior of the print function, this expression, is dependent on the actual type of ppet, not the declared type of ppet. So the actual type is what was stored inside it, which is a dog pointer, not what we declared it as, which is a pet pointer. So that's what's really powerful about virtual functions, and lets us create these dynamic behaviors at runtime, which we consider to be polymorphic. Remember, literally the word polymorphism means many shapes. So this expression has many shapes, many meanings, depending on what's going on over there. It's not the only way to achieve polymorphism, as we'll learn. You can do data polymorphism through generics, which we will do this semester, but this is what most people mean when they mean something is polymorphic. They mean it's a dynamic method that will behave differently according to the kind of thing it's being called on. So that's important. I'm just going to go back to check to see if there's any ideas here. Okay, let's go. All right, the shape being... Oh, right, yeah, no, I see what you mean. Yeah, we literally will do an example like that, where we've got a composition mixed with inheritance and polymorphism. So let's say, for example, you've got a UJ image, and the UJ image has a converter, and it can convert to either PPM or PGM or various other output formats for an image, but the way in which it does it depends on what kind of converter it's been given. Then you've got polymorphism, and we could mixed with composition and delegation. We can definitely do that. So yeah, that's perfectly correct. For logistical reasons, I usually store my dogs in pets. Okay, that makes sense. So the dog loses all of the properties that makes it a dog. It literally forgets everything that made it a dog and only remembers the things that it knew about being a pet. So Dog of Theseus is a good philosophy joke about the ship of Theseus, where if you take all the parts away from something and then reassemble it or replace them with different parts, is it still the same thing? And then, at least in the case of the ship of Theseus, the answer is that the question is flawed, because the universe doesn't recognize what ships are. It only recognizes collections of particles. The idea of ship only exists in the heads of people. So whether or not the ship is the same ship doesn't matter, except to the person who's making the definition. But it's a very good philosophy point there. So pet is not an abstract class. Pet is an abstract class because it's being used to derive dog and whatever other kinds of pets you wanted. So if something is on the pointy end of an is-a relationship, so if the arrow is touching it, it's a base class. It's an abstract base class if it defines a pure virtual function, if it defines a virtual function. So let's just check if it did define a virtual function at all. I can't quite remember. It did, and it's an abstract base class if it defines a pure virtual function. In this case, it's not equal to 0. So yeah, so I wouldn't say this is an abstract base class because it doesn't have that as pure virtual. Presumably somewhere there is an implementation of print that defines some behavior. So I see your point. Well taken. Got it. It's not an abstract base class. If you put the base in there, then I'm happy. Can we please do a tutorial with example later on? Yeah, no. So we're still going to do normal tutorials. And in class tomorrow, I will. Are we running out of time? We are a bit. I'll do a worked example of this exact thing with animals, different kinds of animals, and polymorphism versus overriding versus redefining, and the exact impacts of that. So the most common way of accomplishing polymorphism is to change the functionality compared to the data, like I said. Yeah, this is definitely the most common way of doing it. So rather than, you'll have different versions of overridden functions that will do different things in different derived classes, making those behaviors polymorphic if you call them through the base class. Yeah, it's by far the most common way of doing it. Gets overused a bit sometimes. People, when they first learn about inheritance and polymorphism, they like to make these very deep class hierarchies with lots of polymorphic functions, which can be confusing, and it also is subject to something known as the brittle base class problem, because any decision you make in the base class has to be honored by the derived classes. So if you've called this function print and you've made it a void function, and later on someone wants it to rather be a function that returns a string, they'd have to add a new function to do that. You know, the decisions you make early on can impact future classes. Okay, this is a good question. What's the equivalence of serialization of C++? So serialization is when you convert, in this case, let's say an object into something that can be stored on a drive and then read back later. There's no built-in serialization standard for C++, like there is for, say, Java or for Python with pickling. So in C++, you'd have to manually write it yourself. You'd have to convert your object into a stream of bytes and write those bytes to disk. and then in the function that reads the object, you'd have to read those bytes into a byte array and then cast it into your object type. We will do that this semester. So good question. Yes, that is true. And look, C++ is a very powerful programming language for writing very fast programs, but it's not the perfect tool for all other for doing every job. I don't believe there is a perfect programming language that exists for all jobs, in the same way that there isn't a perfect tool in your toolbox for all jobs. If you try and unscrew a screw using a blowtorch, you're going to have a bad time. If you use C++ for something that could be more easily done with something else, then you've made your life unnecessarily difficult. But it might be impossible to do the thing that you could do with C++ using another language that doesn't give you access to things like pointers. So it's all task dependent. So very good discussion there. So we've still got 5 more minutes. Let's carry on. Okay. Okay. So just for what it's worth, if you've got virtual functions and inheritance, just memorize this. Make your destructors virtual. The reason being is that the lookup for destructors also follows the virtual table then, and then if you delete something through its base class, all of the destructors will run rather than just the base class's destructors run. So in the example that I'll do tomorrow in class, I'll make sure to work through this manually. Right, so here, for example, if we've got a pointer to a base class and we store within it a derived class, and both derived and base have destructors that run, and we delete only the base class, unless the destructor was made virtual, only the base class's destructor will run, which is a problem because then that means some memory isn't being freed or some other resource isn't being released. So rule of thumb, if you've got inheritance, make all your destructors virtual. Just make them virtual. It's just will save you a lot of trouble in the long run. Okay, so casting. Casting is when we manually take control over how a particular value is interpreted in terms of its type. So you've done it before when you cast things to, let's say, double for the purposes of division, or you cast things to integers or whatever it is. You do the same thing with classes as well. Sometimes it happens automatically, and sometimes you have to do it manually. So if you need to do manual casting between types and you've got polymorphism, you're not able to make use of the static class cast over here, because what we're saying over here is we're trying to store a pet in a dog, and we're saying just pretend that this pet is a dog no matter what it is. Like I said, playing with the snake as if it were a dog, you're going to have a bad time. The reverse is totally okay. And if you wanted to cast the dog into a pet manually, that's totally fine as well. So this is called upcasting, where you cast from the descendant type, the derived type, to the base type. The reverse is possible, but you have to really know what you're doing. You have to have extra information about what the restrictions are on the kinds of types that can be stored in these pointers. So firstly, you do it through a pointer like we've seen before, and you don't use the static cast keyword, you use the dynamic cast. Remember, static means done at compile time, and dynamic means done at runtime. If you can only know what the type of something is with these pointers at runtime, because, for example, you could have had a random number generator over here that sometimes puts dogs in the pet and sometimes puts snakes in the pet. You don't know, right? So in general, this can only be done at runtime. So you can do it. You can say, I'm going to pretend that this pet is a dog pointer and treat it like a dog. But if it's not, then very bad things can happen. For example, calling a function that doesn't actually exist in that class will result in a vtable error. So it is very, very dangerous. And the functions you call, having done this, should all be virtual functions. And they call that downcasting. Okay, I think I've actually described this out loud before, but it's basically just the workings of the virtual functions. So you don't need to know how virtual functions work in order to use them. You could be asked about them theoretically, but not in the first semester test, but maybe in the exam you could be asked. But basically it all boils down to this virtual function table, which is basically, you can think of it as an array or a vector or whatever you want to think of it, or function pointers for each class. And they're linked together so that the virtual table of a derived class links up to the virtual table of a base class. The compiler creates it and manages it, and you don't have to worry about it. And inside these containers are the memory addresses of the implementations of these functions. And as a result, if you call from a base class, it will loop up through the hierarchy to try and find an implementation. If it finds an implementation along the path between it and the true base of the hierarchy, it will use that. And if it doesn't, that will be an error. And you're likely to get such errors if you do stuff like this, because you don't know for a fact, for example, that the fetch function is stored in the pet if it happened to be a snake. And then you have a problem. And then that's that. Yeah. So in summary, late binding or dynamic binding, that's where the decision of which function is being called is made at runtime. By default, C++ normal functions use early binding or static binding, but virtual functions use late binding. Pure virtual functions have no definition. If a class has at least one of them, it's considered to be an abstract base class. You can't instantiate abstract base classes, but they're still useful as placeholders in your hierarchy. And as through that, we mean as bases for other classes to derive. If you store derived classes in base classes with stack allocated objects, you could have the slicing problem. So what we do is we use pointers to them instead, make the functions that you want polymorphic and the destructors virtual, and then you can call through the base class to the virtual functions, and they'll behave correctly. And that's that. And I think we're at the end of time, so let's just see if there's anything else there. So this is a question I get asked a lot. I know a lot of languages badly and a handful of languages very well. So I know C++, I know Scala, I know Java, I know Python very well, and I use them all the time. But I know enough about other languages to muddle through if necessary. But your job in life is not to learn a bunch of languages that are all the same as each other, because I can pick up enough Visual Basic to do something if I need to. But I certainly won't waste time memorizing all the differences between Visual Basic and, say, C++. What you should really aim to do in life is to learn a bunch of different kinds of languages. So I also know Haskell a lot and use that a lot. So try and learn a functional language. Try and learn an object-oriented language. You're learning one now. Try and learn a Lisp. Try and learn, try and learn a variety of different languages. That will expand your mind more than learning a whole bunch of very similar languages. So in this tutorial, we'll be doing past papers. Yep. It depends which cast should you do. It depends on the direction you're going. So if you're going from the base class to the derived class, or from the derived class to the base class, will influence whether it's an upcast or a downcast. It's not as important. This is a fair point here. Upcasting and downcasting are not as important as in informatics. Yes, I know they emphasize them quite a lot in informatics. We'll try and avoid them wherever possible and tend to just work through the base class calling pure virtual functions. Delphi was the first programming language I ever made money on. So I love it a lot, but I haven't used it in a decade. Yeah, and Python to me is a great language for very quick, simple projects. Very, very useful. All right, so thanks a lot. We're out of time. I'm going to end the recording. Goodbye to you all. See you tomorrow on Tuesday, and then again on Monday on Wednesday.